Today I'm going to talk about, in context of these two hot BC summer and two wet recently in November, on the perspectives on heat waves and atmospheric rivers in Western Canada. Let me start actually. These two pictures here illustrate what I'm going to talk mostly about. This is the animation. This is the satellite image of the atmospheric river striking on BC part in November of 14th, while this was the fireborn in June, about 4 months apart or so. So briefly, this outline in next 45 minutes, 40 to 45 minutes, what I'm going to talk about. We'll share some of the examples of the recent extreme events, followed by atmospheric rivers, what these events are, and what is the historical perspective of those events, and how they will be in future. Further, we'll talk more about heat wave, including recent heat wave and general climatology. They are important for wildfire perspective, and I'll briefly show you how heat waves influence wildfire. And before the ending our talk, we'll talk more about climate change and extreme events in general for Canadian context as well as global context. So let me start with this too hot heat wave of BC in 2021. In late June and early July of this year, Western Canada and most of the British Columbia experienced a really hot heat dome or heat wave, what we call the higher temperature on the surface, and they shattered many of the recorded temperature. There was fire following immediately the heat wave that destroyed most of the Lytton village in BC, and there was reports that 70% of the certain deaths recorded during BC heat wave were due to actually this extreme temperature that occurred during that part. Environment and Climate Change Canada issued this heat warning for most of the British Columbia. So it was a really historical event that we have not seen before in this part of the world. So it was a big event that considered as one of the extremes in heat wave. So we'll talk more detail in that event in a bit. But about 140 days after that heat wave, almost the same region of BC experienced another extreme natural disaster where we receive a large amount of precipitation in short days, and due to that intense precipitation caused flooding, mudslides across the southern BC. Most of the province was disconnected due to damage in highway and train tracks from rest of the province and actually whole country. And still, I think major highway are under repair, but maybe side highways are working. So it was purely a big event and destructive event in terms of, and this event was caused by what we call a family of atmospheric rivers, meaning a cluster of atmospheric rivers coming back to back without a large window of time that strike on the southern BC and cause this havoc. So this animation map here from NASA Worldview shows the moisture all the way coming to BC through those atmospheric rivers in a series 1, 2, and 3 you can see. And very interestingly, this moisture is coming all the way from tropics and mid-tropics, but all the way up to Philippines, which is like, I was not expecting at the beginning. This is a really long stretch of moistures to come here. I'll talk in a bit what that atmospheric rivers are, but yeah, I want you to start with this animation, I guess, here. So what are the atmospheric rivers? They are the rivers or moisture corridors in the sky. Historically, these events were occurring, but the research and the term atmospheric rivers, that is in practice, is relatively new, like early 1990s. It started the term coming in research community as atmospheric rivers. The first to use this term were two of the Massachusetts Institute of Technology MIT colleagues, Young Ju and Reginald Noel, in their 1994 paper entitled Atmospheric Rivers and the Bomb. That's the first time they used the term atmospheric rivers to refer to the plume of moisture corridor traveling in the sky. Later in 1998, they published another paper where they proposed an algorithm to calculate those moisture flux Meantime, like in the early 90s and early 2000s, there were several of the papers based on experimental year-round experiments as well as theoretical prospects of atmospheric rivers. These events were even occurring before, and in the western coast of North America, generally they were called pineapple expressions, but they occur globally. So basically, these events are the narrow corridor of the moisture in the sky, which have several kilometers of length and less than 1,000 kilometers generally width. They are not like uncommon phenomenon. They occur in any instant of the time. At least there are 3 to 5 of these plumes in either hemisphere of the planet. And they are very important from global water perspective because they transfer more than 90% of all the tropical and moisture from tropics and subtropics towards the mid-latitude. So they are important from water perspective, but they also produce intense precipitation, especially when they encounter orography like topography or mountainous region, resulting in the large amount of precipitation in short period of time, which produce different hydrological disasters. For example, mudslides in mountainous region or flood and there are different techniques to identify and define atmospheric rivers, but generally people use what we call the integrated vapor transport or IVT, which is the measurement of integrated moisture from surface in atmosphere all the way up to, let's say, 300 millibar or some high pressure. Multiplied by the wind component so that we can get moisture flux, like amount of moisture coming at a given instant. Generally, they has to have a direction, which means it has to, generally from tropics and subtropics, they has to direct it towards the mid-latitude because they are moving and bringing moisture to mid-latitude. And geometry, generally length is at least the length to width ratio is more than 2. Since from their impact perspective, we have to have landfall location, like where they make landfall and where is the highest impact. The atmospheric rivers, as we can see on the satellite image, they are like corridors with a major axis, what we call the center of atmospheric river with a large amount of moisture, but also this shape which covers the area. This animation here shows that this plume of atmospheric rivers, just to visualize how they are coming to our regions from tropical areas. So that's a basics about, I think, rivers in the sky or those phenomena. Now let's jump to 2021 event that has occurred in Stockholm, British Columbia. Again, another animation here that shows the family of atmospheric rivers based on IVT coming to BC, but also the contour lines here indicate geopotential height, just to see what synoptic condition was present during those events. As we can see, before the first event that occurred in November of 13-14, there was the frontal wave occurring just below Alaskan part, which stalled the event, making a more intense rainfall in that area. Further, this is still image of that animation for 3 of the major instances on 13th, 21, and 30 of the November. We can see the IVT. Generally, IVT and the duration is used, and recently there has been atmospheric river category or scale based on how long these events occur and how intense the IVT flow is, and there are like exceptional, strong, and so on from laryngeal. This is based on mostly the west coast of United States, but and IVT is more regional thing and changes with the region, so maybe it's not fairly well represented of the BC, but in general, the event that occurred were strong to extreme on this atmospheric river scale. So they were extreme events. And they bring large amount of moisture indeed for the BC. So these are the 2 plots that shows daily maximum precipitation for November of 2021 for 2 of the stations, one in Hope that has a time series of 1975 until 2021, and this is for Mission West Abbey near Abbotsford. What we see here is the I think the highest temperature for both of those stations ever recorded in last about 40-50 years. But for Abbotsford, it's a really high with more than 130 millimeter of rainfall in less than 24 hours, and also more than 112 millimeter of rainfall. Interestingly, I checked after that whether these two high in 1990 November were related to atmospheric river, and yes, indeed, the second highest and the third highest events were also due to atmospheric rivers. So they are the major causative factor bringing the large amount of precipitation in this region. Once we have large precipitation, whole series of natural disasters starts, as I mentioned before. So they were a very significant event this year, and comparatively highest even recorded for last like since 1960 for average per area. But this is not only the event that caused extremes in bases. In 2003, there was another destructive atmospheric rivers that influenced sea-to-sky highway. And also in 2010, the Lakula BC experienced another strong atmospheric rivers. And this is the plot that shows precipitation associated with Delhi, associated with the atmospheric river that is struck on that region, while the red line indicates the IBT. The blue line here is the mean. So you can see like how above average the precipitation was for that day due to atmospheric river. This event was also destructive, and for that reason that occurred in 2010. The synoptic conditions during that event were almost similar to what we have observed in this time too. The green outline here indicates the shape of atmospheric rivers, while the blue solid line is the axis of the event. This dot is the Balakula. We can see like very low pressure system and cyclonic moment just above the Alaskan region during this event. So these events are fairly like common. Then in terms of climatology, how much those events come in BC. So this is the results from my PhD work here. And this is the area where we consider British Columbia and the Panhandle region of the Alaska. On average, British Columbia, this region receives about 35 of those events annually, with highest number of events occurring during fall month, early fall, especially in September and October. November also receive a fairly good number of those events in this region. And so there are like sufficiently large number of events occurring every year. In terms of their trend and how they are changing over time, this plot here shows trend in the number of atmospheric rivers, both in lower latitude regions, which is once we split below 50, about 54 degree north, and the higher latitude regions. On average, the number of landfalling atmospheric rivers are increasing in lower latitude river regions significantly by 1.25 events per decade. That makes about 20% increase during last about 40 years period between 1917 and 2016. This increase is likely due to the combination of change in atmospheric moisture, which can now hold more moisture than before due to global warming, but also in the change in dynamics of atmosphere and the storm tracks, which we'll see in another slide too. So this is the trend on number of atmospheric rivers. Then how much precipitation actually they contribute in British Columbia and Panhandle region of Alaska. This plot also from our PhD work here shows the amount of precipitation associated with atmospheric rivers for our region. What we see here is almost 1/3 of about 9,000 millimeter of precipitation in coastal BC is associated with atmospheric rivers. These are the area with one of the largest annual total precipitation of 9,000 millimeter or more in the globe actually, and 1/3 of them comes through atmospheric rivers in this coast part as well as Caribou and Rocky Mountain region of the BC. However, after Rockies in northeast BC, where total annual precipitation is also low, about 600 millimeter, the amount of contribution is fairly less, around less than 5%. However, on average, they contribute about 13% of the precipitation. In terms of extreme precipitation now, then we define extreme precipitation as the maximum daily precipitation that occurs on each grid over the hour area, and tally whether during that extreme precipitation there was a presence of atmospheric rivers or not. And what we observe is that for mostly coast region and mountainous area, up to 90% of extreme precipitation, or even more, up to 93-94% of the extreme precipitation were because of atmospheric river. So they are the major causative factor for extreme events in this region. So is their contribution changing over time? We can see here the results of zero inflated beta regression model, what we call, with three different coefficients. The first, which is mu, indicate if the mean contribution of atmospheric river to precipitation is changing over time, increasing or decreasing or not, while this sigma indicate the variability in contributes, and the mu is the probability of zero AR related precipitation days. What we see is that zero AR related precipitation days are decreasing, meaning that we can expect more AR-related precipitation days. However, the mean amount of precipitation is not increasing, and it is likely because overall precipitation, if overall precipitation is also increasing, then the proportion of AR-related precipitation will not increase. In terms of extreme precipitation change over time, also we do not observe like regional pattern or significant change over time. Here the blue dots indicate significant decrease, magenta plus sign indicates significant increase, and the other region just shows the coefficient. There is not a good strong pattern to claim it's increasing or decreasing over time. In terms of AR contribution to flooding, they are the major, also like I mentioned before, they are the major intense precipitation producer, but also the maximum major flooding disaster causative factors. At first, my thinking was that spring freshet will be the highest contributing factor for annual maximum flooding, and we may not get lots of atmospheric river related flooding. But this plot here shows for coastal water sites, it's the main causative factor, with more than 90% of the annual maximum flood related with atmospheric river, but also in the mountainous water side and in some of the interior BC water sites, there is annual maximum flood associated with atmospheric river. Further, we take, based on public Canadian disaster database, flood disasters reported in BC for the water year of 1979 to 2016. There were total 32 flood disasters reported. Then we checked the date of those disasters occurred and whether there was a presence of atmospheric river or not. And very interestingly, on 25 of those instances of flood disasters, there was a presence of atmospheric river, making about 70% of flood disasters somehow related to atmospheric river. So this was a very interesting. However, in terms of change over time, there is not significant change observed in air-related extreme runoff over time. So this year we have heard in news and many past that this was a strong La Nina year, and indeed it is a strong La Nina year, meaning the sea surface temperature over Central and Eastern Pacific Ocean is cooler than the average. And that will interact with the atmosphere, resulting in a coupling effect and influence overall weather pattern globally and also including in BC. Generally, we get more wet and colder temperature in western part of Canada during La Nina years. In line with that, we also receive larger number of landfalling atmospheric rivers during La Nina years in BC. For example, we can see here in West and Whisker plots, the black dot indicate mean number of landfalling atmospheric rivers, while the vertical black line is the median line, and we get a sufficiently large number of those events, especially in fall during the La Nina years. So this year is like, in general, from teleconstant perspective or ENSO perspective, also we can expect more of those events. Okay, that's about the historical perspective. What about the future of these events then? This is the results from Gersonov et al. Paper in Scientific Reports, where they have used different models to show how atmospheric river characteristic, including IVT, frequency, and duration will change over time, and how the model predict for west coast of North America between 20° and 60° north, which include from all the way California to British Columbia. And the black solid line here shows the observation of AR characteristics, while the red line here shows the most real, like close to observation 5 models, and the green line shows the other 11 models and their predictions. Although we don't see lots of trend in the early 90s or until 2010, especially after 2010, the characteristics all like IVT, frequency, and duration start to ramp up, and shows the increasing trend, especially between 2010 and 2015, as we see in this map Although there is a large model uncertainty, this is in general with global warming, because when the atmosphere gets warm, we get atmosphere can hold more moistures in line with Clapeyron equation, where it shows that 1 degree Celsius increase in temperature will make atmosphere to hold at least 7.5% more moisture. So this more moisture means more moisture available to form the atmospheric river and make a landfall. Thus, we can expect them to be increased both in intensity, frequency, and duration. Now further this, I'd like to show you this results from Reddick et al. In 2015 paper from JGR Atmos, where it's calculated under 2 different climate scenarios, RCP 4.5 upper rows and the RCP 8.5 lower rows here, how the atmospheric rivers sit and what the influence of the precipitation would be. This plot here shows the spatial difference between future and present IVT on the first map and precipitation on the second map. Looking at those maps under different conditions, what we can see and what's tragic is that there will be significant increase in AR-related extreme events. However, they will be shift further northward, making north coast of BC more vulnerable to intense AR-related precipitation, and then southward. In fact, these models results shows that there may be less precipitation associated with atmospheric river in South Coast and Vancouver Island in future under different climate scenarios. Of course, there are modal variability, and this was interesting in the sense they are shifting northward, and this is likely because of the further northern shifting of storm tracks that brings atmospheric rivers to our region, and this is likely because with warming climate, we may have shift for the northern shift of the Aleutian low pressure system that lies over the Aleutian Island. However, where and how much moisture it brings also depends on topographic barriers, occurrence of mountain, etc. So that's the results about future and historical perspective on atmospheric rivers. But of the same year, we also experienced another end of the extremes, the heat wave, especially in 2021. But these events are also fairly common in that they occur maybe not in the same intensity. So this plot here shows the animation of daily temperature during that period of heat wave between June 23 and early July 2021 over our region using the ERA5 data. This is the graded data, so we may not see those peak temperatures and very localized temperature values, which went up to 50 degree, almost 50 degree in BC. However, it shows like a really high temperature occurring at that part of the region. Several of the temperature records were shattered during that heat wave period. This plot here from Phillips et al. In the paper is still under review, actually shows the maximum daily temperature anomalies for 27 and 28 June over BC and Pacific Northwest region. We can see more than 20 degrees Celsius positive anomalies occurring, which means if some area have temperature of, let's say, 30 degree on average, now they are experiencing all of a sudden 50 degree of the temperature, making this one of the very hot, I would say, hot event occurred in this part. So then what is a heat wave basically? So a heat wave is especially very hot area where the temperature are very high, and generally they are caused by what we call the atmospheric blocking. Atmospheric blocking is like stagnation or slow procession of upward air flow or planetary waves, what we call, and they can be in different shapes. For example, we can see here, this is like an omega shape structure. That's what we call the omega blocks or Rex blocks, or different kind of blocks where the high pressure system exists above us, and it is stalled because of which the surface temperature increases with different mechanisms. For example, your particle collides and long wave radiation is reflected back, increasing the temperature in that area, making high. It's a clear, so you get like more of the short wave converting into long wave, making the temperature high. So we were in the same time when the heat wave occurred, we were working on actually identifying those blocking patterns and relating them with the wildfire information. So to identify those blocking, there are different approaches, but we use 500 hectopascal geopotential height anomalies. Geopotential height is like the height observed to represent the surface pressure at which height it is. And generally, the anomalies which are positive for a long period of time represent those blocking patterns occurring over that particular area. So we define those atmospheric blocking as a contiguous geopotential height anomalies with certain threshold, which is defined based on standard deviation over a longer period of the time. And if they persist for at least certain days, in our case, we use 5 days, and identify those as a blocking pattern or positive persistent anomalies, PPA insert, which represent fairly these heat wave events. This plot here shows one of the events that I've identified using our algorithm, where this blue rectangle indicates the domain used to identify these events, while this black solid line shows the extent of these heat wave events, which start on, let's say this in example, 31 of May in 2016, peak on after 5 days, and end after another few days, like this one. So we are calculating similarly those events in 2021. So we further analyzed 2021 events too. These heat waves, as I mentioned before, were important from wildfire perspective. So we relate those heat wave events with how much fire they contribute in the fire. This plot here shows the probability or chances of fire ignition with the presence of atmospheric rivers. On average, there is the chances of fire ignition increases by a factor of 7, and that value is higher for the northern latitude. A strong interannual positive correlation exists between heat wave and the area borne. Now, and again, it's more significant in the higher latitudes than lower latitudes of Western North America. Further, about 40% of the wildfire with burn area of more than 500 hectopascal are associated with those heat wave or persistent positive anomalies events. And that percentage increases to 60% when we consider really large wildfires with burn area of more than 20,000. So these heat waves of these events are really amplify the conditions favorable for fire burn. And increases the risks, especially in the northern higher latitudes now, where the temperature is also increasing faster than expected. Okay. Again, back to the heat wave of 2021. This is the animation showing the extent of that heat wave that occurred from beginning in June of 3rd week of June, started over the Pacific and extended whole over Pacific Northwest, BC, and Western Canada, and further moved eastward with higher temperatures all the way to central part of Canada, Manitoba, and parts of Ontario, actually. The magenta dot here shows the Lytton village, which was destroyed by the forest fire occurred immediately following this heat wave, and these triangles indicate the fire ignition that started with different size indicating more than or less than 200 hectopascal, and the contour line here indicates geopotential height with a high anomaly, so sorry, high geopotential height over our heat wave events. So this is really interesting to see how this event evolve and expand over time, and meanwhile the fire starts following those effects. Okay, well, using this events criteria, we compare these events to overall other heat waves that have occurred within the month of June and early July for the period of 1979 to 2021, again using the reanalysis database. And this plot here shows the strength of those PPA events, and this is the 2021 events, which is really high in terms of its strength, which is defined as the product of overall area of the event, how much area it covered, but how much was the geopotential height anomalies magnitude, and how long that event process persisted as a product, and this event was a historical in a sense. There were no other events compared to this strength. On average, this event was about 53 times stronger than average of all the heat waves other than this one. It was a 40 times more wider, meaning it covers more than 40% of the area than average blocking events, and it was about 41 times higher than the other magnitude of average magnitude of other heatwave events. So it was a real historical and strong event that occurred during that week. In terms of return period, from the this heatwave perspective, on average, this is the result of a generalized X value fit model to calculate how the return period of the probability of occurrence of such a heat wave on average. What we observe is about 200 years of return period, which meaning is that there is 0.5% chances that the heat wave of this strength can occur in any given year. Can occur in any given year, and not that this event happened and now not will happen for another 200 years. So, but there is a chance of only 0.5% chance that this event can occur in any given year. Okay, so that was about this specific event, and now let's talk more about the climatology and duration of those heat waves and their trend over time in this our area. On average, this plot here shows the number of days when we have heat wave during May and September. On average, about 8 days, any part experiences 8 days of heat waves during this period. However, with a slightly higher concentration over Southeast DC and Pacific Northwest region, and less over Northwestern territory, like Saskatchewan and like this boreal plains. And they, on average, those events are last for about 12 days. However, most of those events are less than a week, and only about 4% of those events have more than 30 days of the duration occurrence. In terms of now the trend, which is more important to see if we wanted to see now whether these events are changing over time and their characteristics and how they are changing. This plot here shows 4 of those characteristics, including the number of heatwave events, their duration, overall area of those events, and the magnitude. What we see here is all those parameters are slightly increasing over time. And statistically speaking, the area expansion is more significant than other parameters. And this expansion area is more important in a sense. Now the more area than before is within the same heat wave, more area is being exposed, causing the larger population on a higher fire risks as well as heat wave risks, and this also putting more constraint towards the resource availability for those events. So this is important, and this increase is likely due to global warming, because not shown here, but what we did is once we calculated those trends based on geopotential height anomalies, we removed those global background warming on geopotential height anomalies associated with it. And again, we calculated the same trend, and the result was that there is no trend observed on either of those characteristics. That means it is that the increase we are observing on their expansion and number or duration or all those parameters is due to background warming, thermodynamical changes in atmosphere associated with global warming. Okay, that's all about heat wave, and now let me talk about climate change and extreme weather events. So this animation here, this animation here shows the change, how a small change in average climate may amplify the change in extreme events. And generally, we talk about like a 0.5 degrees Celsius increase in an average temperature or something, and we may get a perception that, well, it's just a 0.5 degree change or very small change in this average, and there is not big deal. But a small change in average amplify and make the extreme events large change. Actually, in climate science and in the studies of climate science impact, this is, I think, the most reliable prediction that with change or increase in global average temperature, there will be the most significant change in extreme weather events, and that is like the first thing we can reliably measure and predict with a small change, making amplifying the extreme event. So, we have to be careful about how much, on average, we are changing in temperature, average temperature, and how they are amplifying the extreme events. And also, there is a saying, well, there is some say that in a particular extreme event, can we attribute this to a climate change or not? For example, whether this atmospheric event occurred on this year or the heat wave that occurred in June, is that due to a human-caused climate change or not? And there is a general saying that, well, we cannot attribute one particular extreme heat wave to the climate change because climate change and their impact is a more a long-term pattern rather than a one instance of the events. However, that paradigm of thinking is slightly changing, and there are now papers where they actually focus on attributing any specific extreme event to whether it's due to a natural variability or due to a human-caused climate change. And also, people are recommending to do so that people can make plans for disaster risk mitigation and adaptation. So, for example, even this 2021 event where on this paper, as I cited before, with Philippe et al., this is that based on observation and modeling, this event would not have been possible if there would not be a human-caused climate change. So there is more growing evidences of attributing climate change to specific extreme weather events, and there are also new techniques where we can attribute specific events to climate change. So it's not like always that you cannot calculate or say whether a particular event is due to climate change or not. However, what drives those events is an still active area of research. There are different papers coming other days, and these papers are illustrating different mechanisms leading to extreme events. For example, one of the major area of research where this paper shows that in the North American, especially in mid-latitude North American weather, the extreme events are further expanded or magnifying due to Arctic amplification, which is the more like greater warming in the Arctic region than global average. But there are also few papers contradicting with this evidence and saying that there is not sufficient amount of evidence that present Arctic amplification is modulating those extreme events. So this is still an area of research, and we have to further carry out additional research to understand how those extreme events are driven by different atmospheric mechanisms. What are the thermodynamic component of atmosphere that influence those extreme events, and also dynamic components of the atmosphere that influence those extreme events that occur in our area. Okay. Now that we see those connections and I think theoretical backgrounds on how extreme event relates, I'm going to show you a series of 3 maps where we see global trend on mean daily minimum, maximum temperature, and precipitation, which are like the indicator of those extreme events. This plot here, again, from world weather attribution, shows for most of the part trend in the temperature of warmest day of the year, multiplied by the global mean temperature rise, published in 2018 using the 50-year previous year's data. And for most part of the world, except eastern part of the North America, we see like increase in mean daily maximum temperature globally. Actually, maybe parts of India and Africa, I'm not sure why there is not, maybe because of the pollution that has occurring and also more irrigation that may have occurred over India. There is not much increasing trend, but other than this part of the North America, most of the world shows increase in daily maximum temperature. This is the similar plot, but now for minimum temperature. Well, coldest day are getting less colder. Is a signal of those extreme events. And one of the hypotheses of climate change and global warming is that you will have less of cold and more of hot, and that is very well illustrated. And the minimum temperature, daily coldest temperature per part of all the especially in northern hemisphere, is actually very high increase, up to 5 times the global mean increase. We can see over the Canada also the 5 times higher increase in the coldest temperature, generally occurring in winter, so likely because of the more sun, more extent of the snow surface, but also due to GHG, like greenhouse in gases, it's trapped and reflected back, increasing the minimum temperature and reducing that gap between hot and cold. And now this plot here, where we can see the trend in daily precipitation. There is a good variability among global pattern, but in general they are increasing for most part of the world, with higher increase now occurring especially over part of Australia, South America, and part of actually Asia. However, precipitation is a tricky thing because it's influenced by so much other factors. For example, the topography, location, and also the storms that bring, as we have seen before, the precipitation to the area. So this is tricky, but on average, the precipitation is increasing in line with the temperature increase, with up to 28% increase in precipitation compared to per degree global temperature rise. However, with the variations due to local factors. Okay, so that is my presentation on this talk. With this, I want to end this talk with this take-home messages. I'll read those points. It's like these atmospheric rivers play a vital role in BC, but also globally, and contribute significantly in global water supply. They are important not only because they produce intense precipitation and flooding, but also they replenish freshwater aquifers, bring fresh snow, and so those events coming to BC are increasing, with about 20% increase in between last 79 and 2016. These events are expected to increase both in their strength, frequency, and duration. On average, atmospheric rivers contribute about 13% of annual precipitation in BC. However, with the regional variation, in future, this contribution is expected to increase in line with their frequency and intensity. However, that will where this contribution will increase will also be influenced by the storm tracks and the direction of storms coming to this part. Heat waves are significant for fire weather perspective, and the presence of heat wave increases the chances of fire ignition by a factor of 7, with higher latitude regions experiencing more higher fire risks with the presence of heat waves. The number of these heat waves, their duration and magnitude does not show a significant increase. However, their area expansion is significant, posing a larger area and population to higher heat wave risks, including the fire risks. Extreme events are expected to be more common, stronger, and broader, in line with an increase in global temperature. However, further research is required to establish the thermodynamic dynamic response of warming climate. If we can improve the seasonal forecast of extreme event and put attribution or develop techniques, as well as implement already available techniques to assign a particular extreme event to whether it was due to natural variability or man-made climate change, it will provide and enhance our community's ability and decision-making practice to minimize the risks associated with those extreme events. That's all talk. I'm happy to have some discussions on those talks and maybe discuss among all the participants if you have any questions, or we can, like, I may not have answered, but someone else may have answered on some of the questions. And I'm happy if anyone can contribute on those discussions. Thank you. And thank you so much for listening to me. Thank you.